Okay, now let's pick back up where we left off. Our bidirectional motor is complete. The next thing we need on our list, the angular stepper or the sonic sensor. Let's do the sonic sensor. Let's do it next. And of course we're going to create an object for that. And we're going to do new class sonic sensor. And what do we need with our sonic sensor? A blueprint. Talk about consistency, huh? Blueprint. And we'll name it sonic sensor. Alright. That's next. Of course, you know, we have our context for our object, our blueprint. We're going to create our blueprint. And of course, you know, like everything else, it has a private area and a public area, like we described before. And we know from the program that's bad, the sonic sensor has a echo and trigger pin, and of course one of them is an input, one of them is an output. And so we're going to need two pins, and we're going to need a place to store that data or keep track of that data. And so they'll be private, because once we set it, we don't need to manipulate it again. We can set it during the creation of blueprint, like we did the bidirectional motor. So it's pretty much going to be the same thing there. And we'll call that M_ trigger pin. And then M_ for member only echo pin. I think that's the other one. Echo pin, yep. And of course, these are going to be 8-bit values. And then we need the Arduino library, of course, so we can manipulate the pins on the Arduino chip during this process and bring in our library for our standardized data sizes. And then, of course, they're never going to change, so once we set them, so we say they are going to be a constant, just like before. Okay, what else do we need? Let's see. Well, we need to be able to set those pins on the creation of the blueprint. So we need our class name constructor function, a function that's the same name as the class, the constructor. And of course, we're going to require on the creation of the blueprint, hey, what are those two pins? Well, trigger pin number. How about that? And echo pin number. Yeah, that sounds good to me. And just like our bidirectional motor, we need some kind of initialization or begin or startup routine so that we can initialize the pins as output and input or whatever they are on the Arduino board. So we need a begin. It's starting to look real similar to the bidirectional motor, huh? Consistency, and yeah, that's what it's all about. And of course, what we need next is a way to get the data from this sonic sensor. You know, it's a feedback sensor. So, and I looked at a couple things online. Let me see if I can find that. Alright, pause for a second. Okay, I found it online. It shows how to use this sonic sensor. And basically, you know, it's a 3-step process. So we'll deal with that. There's an echo and a trigger pin and this and that and the other. But I was reading through here, and I don't really like what's online too much. I'd like to get the feedback as 8-bit, and to do that we can convert it to centimeters, so we can see how many centimeters away something is in front of the sensor, and that'll give us from 0 to 255 centimeters as far as the sonic sensor goes. So I think we'll use feedback of 8-bit, so that's 8T. We want to get something back. We want our call up to poop us something out, the distance between the sensor and whatever object may be in front of it. And we're going to call that get collision distance. And of course we don't need to give it any information, we just need to get it back. So yeah, that gets us started, that gets us going. Looks pretty good. Now let's go ahead and save everything and create our methods, or teach this thing how to perform these tasks that we're saying, or these abilities that we're saying we have. Let's close this other bidirectional garbage, and let's go ahead and put Rawze on here. And sonic sensor. Okay, just like before with a bidirectional motor, upon the creation of the blueprint, we are requesting 2 pieces of key information: the trigger pin number and the echo pin number. And by the way, and of course we're not going to perform any tasks during the creation, but by the way, we need to take our private members, and let's tab this in, make it look a little better. Take our private member trigger pin and make it ingest the trigger pin number, be set to, however you want to call that, upon creation of this blueprint. And the M_echo private member echo pin, we want it to be set, or to ingest the echo pin number. So that gets our blueprint startup. Upon the creation of the blueprint, we're going to require 2 pieces of information, and by the way, set our private member trigger pin number and echo pin to the trigger pin number and echo pin, what is being supplied. Looks pretty good. Alright, begin. Now, the begin routine for this is going to be, basically to set these pins on the Arduino as the trigger pin is an output, the echo pin is an input. So we go pin mode using the Arduino library, M_ our private member trigger pin, comma, output. That looks pretty good. And then of course we want the echo pin. We need to establish its condition, and that's going to be an input. Alright, so when we initialize this thing and we crank this thing up and turn the key on the starter, hit the starter switch, it's, we'll call it beginner routine really, it's going to set our pin modes. And of course, the only other functionality we need is get collision distance. Now, here's where it gets a little tricky. I was reading through this. Where am I at here? I was reading through this, and here's an example of how to actually get the collision distance, okay? Did you write trigger pin low for 2 microseconds and then set it high for 10 microseconds and then low again, and then read the pulse in with this pulse in function, and then do some math calculatory things. I don't think they're doing it in centimeters here, I'm not sure, but I worked with them before, and I have a little bit better way or a little bit more accurate calculation based on a lot of stuff that I've played with and tested it and stuff. But the breakdown this thing, essentially, it does this thing in 3 steps, like I said. Okay, it ensures the trigger pin has settled into a settled state. That's these 2 lines of code, okay? And then it says to bring the trigger pin high for 10 microseconds and then low, And then, of course, to do a pulse in command with the Arduino library to measure when the echo pin goes high after that. Basically, ensure the trigger pin is in a stable state. Send out a ping, like in a submarine, like ping. It sends out a ping. It sends a ping, and that command that sends a ping is these 3 lines of code. And then, of course, it waits for a response, a pong. Ping, pong. Just like a sonar, just like a submarine, just like a, radar system. So, I think that's what I want to do. I want to, that very accurately, generally describes what this thing is doing. So, I think that's how I'm going to code it. I'm going to program it this way. And to code it this way, I need to fix my camera. There we go. To code it this way, I could just simply say, instead of all that digital doodle up, I could just say, ensure trigger pin has settled. That's English. That's not programmerese. And of course, the only way to make a command that actually does something with that is to turn it into a function, of course. So we'll make it a function. And then, of course, the next step would be to send out a ping. Send ping. That sounds good to me. And then, of course, we need to measure what's coming back, which would be a, ping pong, would be a measure. Wait, measure a pong. How about that? Measure pong delay. How about that? Yeah, that sounds good. Now, if my program looked like that, I could tell what was going on. Get collision distance. Ensure the trigger pin is settled. Send out a ping. Measure pong delay. That's English. That's something that's readable by someone who's maybe not familiar with what's going on here. At least gives you an idea of what might be happening. So, how do we turn these commands I just made up out of the blue into actual, things that happen? Well, we do know that to send out a ping, we need these 2 lines of code. And that's great. We'll use these 2 lines of code to make that command. And then we'll, to do the ping, we'll use these 3 lines of code. And to do a pong, we'll do a pulse in, but I'm going to use my modified kind of version of that. Maybe, yeah. So, and I'll go get that when we go to that part. But how do we turn a command we just made up out of the blue into a actual working something? Well, there's a couple ways to do it. We can do it here because if it's only ever going to be used within this contextual space, which happens to be a function in this case, we could actually build these functions inside here if we wanted to. Or we can make them private to the entire object. And I think I want to do private to the entire object because it's more appropriate usually. Unless you have some specialized thing, it's more appropriate just to make it part of the object. Object's blueprint as a private part of the private collection. As things it is able to do, or commands is able to perform. So I'm going to go ahead and put a _, members only, in front of these names, just so that I know, and that's good programming practice, as a general rule, that they are private only to this blueprint class, object, whatever you want to call it. And of course, to make them into something actually usable, we'll go back over our header file and we will put them in the private area, just like we made them. And of course, C++ requires in any function what you want it to eat, and in this case, we don't need to eat anything at all in any other one of these commands. But we always have to define what it's going to give us back or poop back out. So in the case of ensure something happens, we don't need any information. Just go do that. So we're going to say void send a ping. We don't need anything back. Okay. But measure pong delay, a little different. We need some data back. We need that measurement value. So we're going to, and of course I want to use centimeters, 0 to 55. So we're going to 8-bit. So int8_type. So 8-bit data. Give me back some 8-bit data when we do a measure pong delay. And that's how we turn commands that we make up into actually working things. Now, if we look back here, we will see we're not even getting any errors anymore. But, like I said, as you know, described over and over again, a blueprint is an idea. It is not how to do something. So to translate this idea into how to do it, you do it in the CPP file. So we go to our trusty source implement method because I like Eclipse. Select all, and you can manually type this out. By the way, you know, I keep using this automated function, but you can manually type out this line. You know, sonic sensor blueprint measure. You know, here's how you do this. Here's the context for this. You know, private function or whatever you want to, you know, manipulate. Ensure trigger pin is settled. Measure send ping and measure pong delay. Now, that's going to put life to our homemade custom descriptions of what we're doing in this collision routine. And just like the example, there's nothing wrong with this example. It's just that I wouldn't code it this way in my own programs. Copy and paste. Rawze did some copy paste programming. Oh my god. No, not really actually. Alright, so, and of course we have a private member trigger pin, which is this guy right here instead of their example name. And that's it. That's what we need to do to ensure the trigger pin has settled. Of course, how do you send a ping? Well, their example is exactly what we need to do actually, which is here. Digital write, trigger pin high, wait 10 microseconds, and then set it low again, so that we go ping, send that ping out, that sonic sensor. Copy, paste, and then of course we need to use our private member data here and here, and that of course uses the Arduino standard library to do those things. And then of course measure pong delay. I'm going to go get that portion of code from what I've already played with in the past rather than using their example. You know, their example's okay, but what I've got gives me centimeters, it gives me 0 to 55. So I'm going to use that, and let me go find that and come right back. Okay, I went and found it. Now, I don't know, maybe my beer is talking or what's going on, but I'm having fun. Anyways, to measure this pong delay, you know, they've got this pulse in. You know, if you look at that example, they got this pulse in, echo pin high, and we're going to use that part of it. You know, this is how we get some data back by using that Arduino function pulse in, which measures, you know, hey, how long did it take before this signal went high or whatever, from the Arduino library. And this pulse in, of course, we need the echo pin, our private member echo pin, instead of their description. And if you highlight over this and I move my mouse over this, I can see that, or if I open declaration, let's go there. It says unsigned long, and that's what it's going to poop. It's going to spit back out at us an unsigned long. What's an unsigned long? It's a 32-bit value. So it's going to send us a 0 to 3.1 million blah, 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 insanely high value. It's a 32-bit long. It's able to actually send us back. And it's way too big a data for us to make 8 bits. So we're gonna chop that down and scale that down and turn that into some centimeter value, something we can actually measure with a ruler. So how we need to do that is we need to do some math. And so we need to divide that pulse in from 2 point something million down to some, you know, 0 to 55 value or whatever. And if we just divide it as an integer, a whole number, we're going to lose all the decimal places. So to get a more accurate reading or way to do some math with a number, let's say you got a large number, you want to divide it by 0.0002, you know, 0.0 decimal something, you need floating point mathematics. And to get floating point mathematics, you simply have a float in C, C++, you define your data type as a float. Well, this data type is something different. It's a big, large number. But I can say, hey, I want a float, and I want the measured we'll call it measurement, equal to this big, huge number converted to a float. How about that? But since we're creating the variable and we're assigning it and we're sending the data from this pulse in, the response from this pulse in to it directly, all in one line, we don't need to redundantly say float, because the compiler is going to know you want this pulse in to become a measurement that is a float value. It will convert it along the way. So there's no reason to put redundancy in there. And if you did put the redundancy in there, if you did leave this in there, I found out that sometimes, every once in a while, when you look at the raw assembly language code for some of this stuff, and I've done a lot of that, sometimes it will actually, this forcibly converts the result of this into a float before it assigns the variable. And every once in a while, you'll see this forcibly conversion, this conversion, say, I specifically want this converted before I store it. It'll convert it, it'll store it, and then it'll check it to see if it's floating. And so it just adds code. Once in a while it'll do that. Sometimes it don't. Sometimes it does. So I omit it. I say, hey, the compiler's smart enough to figure that out. So that makes sense. So now we have a floating point decimal. We can say, hey, measurement add 0.001, and it'll make measurement plus 0.001. It'll do the decimals. It'll do the floating point precision. And what we're going to do is we're going to now take measurement and convert it into something more reasonable that we can send out as an 8-bit data structure. And we're going to say equals measurement divided by 5.8 divided by, and then the result of that, the result of measurement divided by 5.8, we also want to divide it by 10 to scale it down again. And then, of course, I will use a comment because this is kind of convert raw signal to centimeters. One of the rare occasions I use a comment. Now I could, how do you spell centimeters? There we go. Maybe I could make a function out of that. Like we did up here, convert to centimeters, but it's starting to get a little redundant. I think just a comment would suffice in this instance. So I'm going to leave a comment in there. Convert raw signal to centimeters. And then the next thing we want to do is we want to give back, or we want to say, hey, what are we giving back here? What am I going to return or poop to whoever has called me, which would be down here. So we say return what information? Return, and of course we can say, hey, convert this to a uint8t data type measurement, because it's going to be scaled way down. It'll fit in an 8-bit data type. Now, this inherently, again, is a double conversion. This is saying forcibly convert measurement back into a unsigned integer, and by the way, return an unsigned integer. It's almost the same as saying this and forcibly doing it. We can do that for aesthetic reasons, but like I said, I tend to omit it because it's obvious return measurement is going to return an 8-bit integer to the compiler anyways. So we prevent our redundancy there. Because it's fairly straightforward and obvious. That looks pretty good. So measure Pong delay is going to be get the pulse in as our measurement. Measurement equals measurement divided by 5.8 convert raw signal to centimeters, and then return measurement. So that gets us pretty close without too much computerese, actually. Get collision distance is going to be ensure the trigger bin is settled, send a ping, and measure Pong delay. And then, of course, we need to return a value because we're saying, hey, whatever's calling this function needs to get some information back. And we can just say right here, we can say return measure pong delay, and that will forward this data, which was calculated and determined here and spit back out here. We'll forward that result out here as this information and forward it to whoever or whatever system source or thing called this function, and that'll work just fine. There's a problem with this though. It's not in code. It's with this thing. This little guy right here. This little, not the motor, but the sonic sensor. This little two eyes. This transmitter, receiver, the sonic sensor. Ping, pong, measure the pong. This thing is inherently very unpredictable and kind of quirky. You put a piece of cloth in front of it, it may not even see it because it's working with sound. It's not working with the light. It's not working with what we can see. It's working with sound. Sound passes through a lot of things. You bounce it off a hard object, it's going to see it. It's going to get a very consistent, accurate reading. A softer object, it's not going to get a consistent reading. And I can say right now, this thing here, if you have something in front of it, let's turn this camera this way. If you have something in front of it directly, it'll see it. Okay, but if the something is turned, it's like at a high angle, the sound will bounce, and instead of coming back, it'll bounce and go that way. And so it doesn't really see too well some things. And so there's a lot of inconsistency in this sensor. And so what I found by playing with that, I got another robot over here. I've been playing with that sensor a lot. And what I found is if you take the measurement twice, if you do it 2 times in a row, and you get the same value back 2 times in a row, you can pretty much assure yourself, it's pretty consistent, so that's probably fairly accurate. But if you take a measurement twice and you get back 2 different numbers, most of the time it's some erroneous static data or static signal that's just unstable. So you can't really rely on it. So what I do, or what I did with the last project I did with this same sonic sensor, to get my collision distance, to get it more accurately, to dial out some of the noise. You don't want all the noise dialed out. You can't prevent all of it. You'd be sitting there forever waiting for a signal. But you can dial out some of it. You can reduce the amount of garbage feedback just by taking the measurement twice and comparing the 2 measurements. In other words, measure it, remember that information, measure it again, and then are these 2 equal? If they are, it's probably good data. If it's not, then store that over here and then measure it again and see if they're equal. And if not, well, save that and then check again. And once those 2 are equal, in other words, you keep checking until you get this one and the consecutive next one equal to each other, and then you can rely on that. So that's what I've been doing, and that works quite well, actually. It's not perfect, but it's a whole lot better than just simply relying on this data, and most time it's, half the time it may be garbage. So how do we do something in multiple succession? We do a loop. We make a program loop. So we can make a program loop with a do statement, do over and over and over everything in this context, as long as or while something is true. Okay, and what is true? Let's say our feedback is equal to our last feedback. That sounds good. Or last measured feedback. Yeah, that looks good. And then we can stick this in there without the return delay, without the return, of course, because we're not going to return until we actually get a confirmed signal. Now, what do we want to return? Obviously, once I get it, I store it over here as the last feedback, and then I check it again as feedback, and they match. Well, that feedback is valid information. So we can return our feedback. Yeah, so we can return the feedback information. And of course, when we get this measure pong delay, we say that is our feedback is equal to what we are measuring right now. What we measured is our feedback, and of course our last measured feedback. Once we set that, we can say our last measured feedback is equal to feedback. Okay, and we can store that, but we need to do that after we make our check to see if they are equal. And by the way, to compare, you need 2 equal signs, not 1. Otherwise, we'd be setting feedback to this. So we check feedback. We see if it's equals our last feedback, and if it's not, I think the beer's talking. Good old Guinness Stout. Anyway, we take a measurement, and as long as those measurements don't match, our last measurement doesn't match what we measured last time, we keep going. And how do we save what we did last time? Well, at the top of our do loop, we say measured feedback is equal to our feedback. There we go. So now we're going to store, in other words, we're going to store this over here to the last, and then take a new reading, and then see if the 2 readings match. And then we're going to store this over as store what our new reading was over as last again, and then take a new reading. So that will work, and that will work. Now, it's giving us lots of problems and complaints because we never defined what feedback is. We want feedback to be the same data storage type as what we're getting back from that measured thing. So we say feedback, and we say last feedback, and we say they are data type 8-bit. There we go. Yep. Yeah. So now that gets us a valid place to store those and their names. But when we do this, when we run through this, the very first time we run through this, okay, the very first time this executes, these numbers, if we don't set them to something, if we don't preset them to a value, what happens is, they're going to be random. Whatever memory space the compiler and the processor and the RAM, whatever memory space and RAM that thing chooses to store this information, or however it chooses to store this, if we don't preset it, whatever was there before, it's going to be some random value that we don't know. So we're going to create a problem. Let's say it just happenstance that last measured feedback equals to what we just checked it. It's going to make it valid, even if it might not be valid. So we don't need that. So we need to preset these to empty or 0 so that we don't get some invalid garbage upon entering this routine the first time. So that will make our get collision distance. We're going to get a couple variables, feedback and last measured feedback. We're going to make sure they're equal. We're going to make sure a trigger pin is settled, send a ping, wait for a delay, and store that as feedback, and then check. Was this the same as last time? Nope. Make it the same as last time, check it again. Nope. Make it the same as last time, check it again. Oh yeah, I got two in a row that were the same. Well, if they're in a row the same, it must be good. Just return the feedback. That's how that's going to work. So a little bit of logic, a little bit of stuff going on there, but not totally uncomprehendable. I think it's fairly good. It's got good integrity. You can see what's going on. A little bit of thinking about it would let anyone know, okay, this is what it's kind of doing, and it's in a decent format where we can read what's happening here. So I think that's good. Without this kind of imagine if I had just done this right here. This kind of crazy, this kind of crazy, imagine if I had just done that and then return whatever result. It's like, what is this doing? It's like, I don't know. I'd have to include those paragraphs and explanations, and the hell with that. There we go. I think that's about it. Just about to call it good, but I do want to address this one little thing right here. This is going to keep looping until we get two values that are the same. What happens if it's teetering on, like, you know, let's say it sees something 12 centimeters away and it's sort of at an angle, or, you know, it's kind of unstable. And what if it's teetering right on 12 or 13 or 11 and 10 or 20 and 22 or 20 and 21? You know, if it's teetering right on something, it may sit there and teeter unnecessarily on a value, or it may check and check and check and check and check, and we don't have any way. It has no way to escape this if it doesn't get two readings that are exactly the same consecutive. So I think we need to have some way of saying, hey, after so many readings, you just call it good. So I think we need to have a counter in here, and I think that would be important. So let's also say, hey, number of tries, and we should maybe set that to maybe, I don't know, we'll set it to 10. And of course we can do an enumerator, so we don't have a value there. Max number of tries, retries equals 10. That sounds good. And then of course we'll just call this retries. So what we're going to do is we'll just decrement retries every time this thing checks and it fails and it loops again, equals retries minus 1. Of course, in C++, there's a shortcut method to do this. You know, if you're going to decrement 1 or increment 1 or increment or decrement a value, especially by 1, there's a shortcut method that actually there's another way to say, to decrement a variable, and that's just to simply do this. Retries. Or subtract retries by 1, and it's sort of a shortcut method. If we want to add 2 retries, count upwards, we would do this. And I thought I would also mention, while I'm at this, I'm going to do it this way. So we can decrement retries by 1 every time this thing loops, and of course it started out at 10. So why don't we say, while they're not equal, and we'll put this in parentheses, or, and the or symbol for a comparison is 2 double vertical slashes, the tall vertical slash above the enter key on my keyboard here, most keyboards. And, which is 2 and symbols, and retries is greater than 0. There we go. So now, basically, it'll run down through here over and over and over, and it'll decrement retries. And if retries reaches 0, it will go ahead and continue on and just give me whatever the last reading was. So this prevents it from, making 100 tries or 1,000 tries or 5,000 tries. If it just can't, come up with a solution, this keeps it from hanging up our entire program for unknown quantities of, time. So large quantities of time. Let's say you have a piece of cloth that's waving around in front of it, it's always going to be moving, always going to be changing. So not a good scenario to end up in. So at least after so many tries, it just gives up and just gives me feedback, which is better than nothing. Better than not making a decision at all. So that looks pretty good. Yeah. Let me fix this. I just noticed that. What good is an enumerator if you're not using it? There we go. I think we have everything written for our sonic sensor. We have a way to get our distance. We have an initialization routine. We have a way to assign the pin numbers to that sensor. Some storage space for such things. And we have some feedback. Here's how you do those things and how you get that collision distance. Here's how to do it. that sums up the sonic sensor.